So we've got our last section in chapter 5, which talks about additional properties of the binomial distribution. So for this section, there's no handout. You'll see there wouldn't really be much to put on a handout because we're just going to make some tables and some graphs. So to start off with an example, let's suppose we are going to flip a coin 6 times. I know, super exciting. That's how these statistics experiments are. We're going to make this a little, this coin is on fire. There we go. It's on fire. We're going to flip it 6 times. Now it's more like a chemistry experiment. And we're just going to count the number of heads. So if you remember success or failure, success just means you get the thing that you were looking for, right? So the coin landing heads will be a success. So we've got P, Q, and N. P is probability of success. And this is a fair coin. It's not a, an unfair coin. It's going to land on heads 50% of the time and tails 50% of the time. Right, so it's a fair coin. So the probability of success then is going to be 0.5, right, or 1/2. It's 50-50. Remember, Q is just the probability of failure, and this is a binomial distribution. So these are binomial experiments, meaning there's 2 outcomes. When we add these 2 probabilities together, we have to get 1. So Q is also going to be 0.5. N is the number of trials, which in this case is 6, so N equals 6. So what I want to take a look at first is a probability distribution table. So I've got this table here. What we want to do is consider R would be the number of successes. So if you're going to flip a coin 6 times, getting heads would be a success, so you could get 0 heads all the way through 6 heads. That's all the outcomes we could get, which means that if we calculate these probabilities, and I don't know why this is right there. It doesn't need to be there. So we want to calculate these probabilities, and if we add, when we get done, if we add up all these probability numbers here, we have to get a total of 1, right? Because this is all the outcomes of our experiment, and the probabilities of all those outcomes have to be 1. So I want to have us practice rounding also, round to the thousandth. So that's the 4th decimal place. So just a quick review here. The way the numbers systems work. This is the ones place, right? And then you come over here, you've got the tens, the tenths, hundredths, and then thousandths. Because really every number here represents 1 over 100. Or, geez, Kurt, 1 over 10. This is 1 over 100. This is 1 over 1,000. So as an example, let's say I have 0.2. Well, 0.2 is 2 over 10, right? That's how this whole thing works. So this is the tenths place, hundredths place, and thousandths place. All these numbers are almost impossible to say. I hate saying these numbers with a thus at the end. It's like difficult to say these numbers without spitting all over the place. But anyway, 0.2 is 2 over 10. So if you have something like, I'm going to add another one. Again, this is just review. If I have 0.23, well, this makes it out to the hundredths place. So I have 2 tenths plus 3 100ths, or you could just say it's going to be 23 100ths. Right, where if you have a number over here, this is the ones place, then the tens place. So if you have something like this, just put another couple numbers here, 15. So if you have a number like 15.23, this is the ones, you have 5 ones, 1 10, but over here it's all fractional numbers. To the right of the decimal is all fractions, right? 2 tenths, 3 100ths, or 23 100ths altogether, right? Because 2 tenths is like 20 100ths, right? 2 over 10 could be like 20 over 100. So we want to round to the thousandths place right here. So we're going to round to the third decimal place. I hope I said that earlier. I might have said fourth, but let's go to the thousandths place, right? So we'll go tenths, hundredths, thousandths. So when we round to the thousandths, we're actually going to need to look at this spot right here. So again, just a quick review here. Let's clean this up a little. And let's just say, because we're going to have our numbers are going to be less than 1. So I'm just going to do one for practice. Okay, so we went around to the thousandths. So we've got tenths, hundredths, thousandths. So we're going to round to the third decimal place. So remember what we do is we look over here to the next one. We look to the next one. We look over here, and this one's going to tell us to either leave this one alone or move it up 1. And we'll just use traditional rounding. Some of you will take physics, and not all physics classes, but there's better rounding if you really use a lot of data. There's a better technique that you'll learn later. But standard rounding, the way it's almost always taught, is this. Look to here, and if this is 5 or more, we move this one up. If it's not, if it's less than 5, we leave it alone. So in this case, it's 6. So if I round this to the thousandths, the number would be 0.235. Okay, so keep that in mind. So what I'll have you guys do is, I'll get one started and have you guys do the rest. Just make sure you can do these okay. And what we want to do is use our calculator. For instance, if I wanted to figure out what this one is right here, I would have to use Binomial PDF, right? Because basically I'm figuring out the probability that R equals 3, right? The probability that R equals 3 successes. So what I would do, I have NPR 6.53. And when I do that, I'm getting 0.3125. So I want to round to the thousandth. I want to round right there, which means if I round there, I'm going to get 0.313. Okay, so for each one of these, we can just use Binomial PDF. So what you guys should do is just press pause and go in and fill these in, and then come on back. So hopefully when you filled these in, you got these numbers here. And you notice there's a symmetry here. There's a symmetry in the table. And one of the homework questions, even I think somewhere in chapter 5, maybe 5.1 or 5.2, asks you to look at the binomial distribution table in the back of the book. And they ask you a question about the symmetry. So this symmetry will be just like this whenever p equals 0.5. And this symmetry is reflected in the graph. If you, instead of using a table, if you put this into the form of a graph, which we'll look at in a second, you can see the symmetry there too. Now remember, in our book, they're going to call the graph of this, when we put this in graph form, a lot of times our book calls it a probability histogram. It's kind of unfortunate to use the word histogram because we've been kind of conditioned to believe a histogram is kind of that nightmarish graph we make, right? When we made a frequency histogram. A probability histogram is nothing, it's nowhere near as involved. It's basically just putting this into a bar graph. So when you see probability histogram in this chapter, don't think of that first histogram we made in chapter 2. We don't need to know about class width or anything like that. A probability histogram, or what I typically call just the graph of this binomial distribution, is just this. It's just taking this and putting it in graph form. So when we do that, when we put this in graph form, these outcomes, these are going to go plotted, they'll be plotted along the horizontal axis, all the possible outcomes. And then we're going to plot along the vertical axis these probabilities, the vertical axis, which in algebra class you call it the y-axis, right, the vertical axis. So we need our vertical axis to go to at least 0.313 because this is the biggest one we've got here. So when we make a graph, we have to be able to show 0 through 6 on our horizontal axis, and our vertical axis has to go to at least this number. So I started making the graph here. We have our outcomes here. The outcomes are plotted along the horizontal axis. And we don't need, when we made a regular frequency histogram, a lot of times this would be a number line where this spot right there meant like 1.279 or whatever. Here, these are just individual outcomes. So we don't really need to think of this as a number line. So I definitely don't need to make, one of these kind of, to show that the number line has a break or anything like this. This is not a number line like we have in a histogram where it's a real number line, right? This is just showing our outcomes, so we don't need anything like that. So we've got the outcomes here. Now I have to list the probabilities here, and we look at our table to see the biggest number we need, and it's 0.313. So I would probably just go to 0.4 just to make it easy. So since we're doing this by hand, it's easier to do it like this. Now, of course, usually these are only done by hand in this class, the first year stats class. Beyond this, you'll probably use software to do all this. But like we talked about, you kind of, to really develop the intuition, it's good to do these by hand the first time around. So then what we have to do is we basically make a bar graph. It's going to look just like a bar graph, but the difference is the bars will actually touch like a histogram. So when you look at this from a distance when we're done, it will look like a histogram. Remember, our book will call it a probability histogram, but I'm just going to call it a graph of our probability distribution, or I'll call it our probability distribution graph. Like this would be our probability distribution table. So just want to remind you, because that phrase brings confusion sometimes when students read probability histogram and they think of that bad experience in chapter 2, making a frequency table and then a frequency histogram. So don't think of it like that. It's just, we're going to show a graphical representation of this right here. So I'm just going to make the bar heights correspond to these probabilities over here. So I drew the first 3 here. This just has, this height is 0.016. So you can think of it like if this were 100, this would be 16. This is 0.094. So since this is 0.1, this is going to be pretty close, 0.094. This one is 0.234. And then I just keep on going. So the next one is 0.313. Should be just a little bit above the 0.3. And just remember, we're doing these by hand, so they're not going to be perfect, but we can make them pretty good. And then we can use the symmetry to get the rest of these. We just want to make the bars have roughly the same width. I mean, with software, they'll have the same width, but doing it by hand, we just want to make it as close as we can. Just extend this a little bit. Okay, so it's not perfect, but we do it by hand, it'll look something like that. Now remember, what we want to do is make this really easy to read. So also, I should probably mention, typically you'll have a little gap here, but not always. It sort of depends on the software. But we need to label this, we need to label this, and then we always need a title up here. So these represent the number of heads. So I should just write, I'm just going to write that. These are the number of heads. And then, of course, here, these are probabilities, right? It's a probability. So since we're making a a graph of a probability distribution, we need to write probability. And then the title, I guess I'm just going to say graph of a binomial probability distribution This is a very wordy title, so I'm just trying to cover all the bases so we see words that we're familiar with. And I would probably even do this. I guess we could say for a fair coin, but instead I'm going to do this. I'm going to give more details because of what we're going to do next. I'm going to say P equals 0.5, N equals 6. So when you see this P equals 0.5, when that happens with a binomial probability distribution, you're going to see the symmetry that we see in the table. But what we're going to do next is see what happens to the symmetry in the table and also reflected in the graph when this changes. And then we'll talk about how skew comes into play. So that's what we're going to look at next. One thing I just thought of though, let's make a little note here. I just want to make this official. I'm going to say note. When P equals 0.5, the graph of the binomial distribution will be symmetrical. Okay, and also just want to make something else clear, just to make sure we're good with binomial PDF and binomial CDF. If I were to ask the calculator binomial CDF, using the CDF, not PDF, and I said 6.52, what is this asking the calculator to do? Well, remember it's the binomial CDF is cumulative function. Whenever you use binomial CDF, it means always start at r equals 0 and go up to and including r equals this number, which is 2 in this case. So really what this means is I'm going to take binomial PDF 6.50 plus binomial PDF 6.51 plus binomial PDF 6.52. So remember these are NPR. So basically I would take these numbers up in the table, and if I ask the calculator this question, it's basically going to take these numbers here and add them all up. All right, so I just want to make sure we're clear on that. If you ask the calculator this question, you should get the same thing as if you add these three numbers up, because that's what CDF is going to do. And remember, that's actually a weakness of this command. It forces us to start at 0. Then it goes up to and including 2. But it'd be a more user-friendly and practical command if we could tell it where to start. But just remember, binomial CDF always starts at r equals 0. Now, you're probably thinking, oh my God, Kurt, you're reading my mind, because I know what you're thinking is, well, yeah, but what if P is not equal to 0.5, right? That's what you're thinking. And you're thinking, I sure would like to see a table and also a graph. Well, today is your lucky day, because that's exactly what we're going to do. So let's suppose the coin isn't a fair coin. So we've got this situation where we've got a coin that's not a fair coin. There's something that's not right about this coin. This coin tends to land on heads more often than tails. So let's say it lands on heads 80% of the time. So if P is 0.8, Q is going to be 0.2, right? It's going to be 1 minus. Remember, Q equals 1 minus P. All right, Q equals 1 minus P. And that's because P plus Q always equals 1. Right? Because this is a binomial distribution. So with a binomial distribution, there's only two outcomes. And the probability of success is P, probability of failure is Q. Those are the only two outcomes. So when we add them together, we have to get 1. Okay, so what we want to do then with this new information, we want to still kind of do the same thing we did before. We want to come up with a table and then take the values from a table and turn it into a graph. So if I start to make the table, it looks similar as what we had before. We've got our outcomes here. These are the possible outcomes, and these are the probabilities of those outcomes. Now remember, we're counting landing heads as a success, and the probability of success is 0.8 or 80%. So we would expect to have a lot of the probability kind of up here on the upper end, right? Because there's an 80% chance of success. Think of it like a free throw shooter. Somebody who makes 80% of their baskets and they're going to take 6 baskets. They're hardly ever going to make 0 baskets, right? And it's going to be unusual for them to make only 1 or 2. They're usually, if they make 80% of their shots and they're taking 6 baskets, they're usually going to be making, 3, 4, 5, or 6, right? Most of the probabilities will be here. So what we have to do, let's do the same thing. I'm going to do the first one, then have you guys try them. Just make sure, let's again round to the 3rd decimal place, the 1,000th place, right? Just get practice with the rounding. So if I want to figure out this one, I just have to plug in binomial PDF, NPR. So we got 6.8 and 3. And if I plug that in and round to the 3rd decimal place, I get 0.082, which means this person's got about, if I change the decimal to a percent, about an 8% chance of making 3 baskets. And then most likely that will go up here because they're pretty, if you think of a free throw shooter. Again, I know this is, I introduced it as a coin toss, but most people are not as familiar with it with an unfair coin as they are with a free throw shooter. So that's why I'm sort of switching it here. But it's the same either way. But the person who makes 80% of their free throws, or a coin that lands heads 80% of the time, out of 6 trials is going to have a lot of these upper numbers and not too many of these. So go ahead and see if you can fill this in. Remember, don't wait for me. You have to do it yourself and then check. Okay, so take a break. Not take a break, but press pause and go ahead and fill these in and then come on back. Okay, so hopefully this worked out, and you notice we have pretty small numbers here. If you run to 3 decimal places, I'm just going to put 0.000. This is how the book does it also. So we're not putting 0. We're not saying it's impossible. It's just 0.000 rounded to the 3rd decimal place. This can happen, obviously. It's just not as likely. And then you can see that this person, if you're flipping a coin that lands on heads 80% of the time, and you flip it 6 times, there's about a 39% chance you're going to get 5. So hopefully these worked out for you. If not, remember just using binomial PDF, NPR, P in this case is 0.8. N is always 6, so these two stay the same. The only thing that changes is the number of successes R. R equals 0, 1, 2, 3, and so on all the way through 6. So now what we want to do is we want to take this information here and display it not in a table, but in a graph. So as you start making your graph here, I can see the horizontal axis is still going to be the number of heads. It's still going to go from 0 to 6. Now the probability for the vertical axis, now I've got to cover 0.393. So it's still small enough where I can go to 0.4 and it will work. But whenever you make your vertical axis, we just need to make sure that it's able to cover all the numbers here. So in this case, I'm just going to use 0.4 again. So we've got this, then I'm going to fill in some information because we always want to label each axis, right? So we've got the horizontal axis, the vertical axis. And again, this will be the number of heads. And sometimes people will put R here or X. And then if they do that, then they'll also put something on the vertical axis. They'll put P of R or P of X. So you don't have to put that, but sometimes in the title it would show what this is, and then all you'll see here is R, and all you'll see here is P of R, because this really means the probability of R. So it's just something you'll see occasionally. So for this title, I'm going to write it like I did the last title. So now we have everything labeled, we just have to fill in the information. So this first one is not even going to show, right? There's nothing to show here. And the second one might be like the width of a pixel. It's going to be really small. So beyond that, then we can start to show these. So I'll just fill in. So for 0.002, maybe just like the real thin line here. They got 0.015. So that would be able to be shown. 0.015, then we've got 0.082. And then for 4, we've got 0.246. Again, we want to make it looks like a histogram. The bars are touching, which is what we want. For 5, that's the big one, 0.393. Then for 6, we've got 0.262. Well, okay. Not perfect, but I guess it's okay. All right, that should be right in the middle there for 6. So you can see the probabilities here have been pushed over here. When you've got a high rate, 0.8, sorry about that. I know you guys are probably screaming at the computer. Kurt, you're being old again. Oh my gosh. It's not easy to keep track of stuff when you get old like me. So, all right, so peak was 0.8, and we can see that the probabilities here, if there's a high rate of success, which there is here, the probability of success is 0.8, you're going to get a lot of successes right out of 6 trials. So that's reflected in the graph. So when you look at this graph and we talk about skew, you can see that this graph has a tail to the left, right? So this would be called skewed left. It's skewed left, which will always happen when you have a binomial distribution and p is above 0.5, you're going to have a left skew. So the little note here just mentions that this is skewed left, and this always happens with a binomial distribution when p is greater than 0.5. The probability of success is more than half, so you're going to have the bulk of your probabilities over here in the high end. Now what if we had the opposite? What if this were like p equals 0.3, so the probability of success was less than half? Well, with a low probability of success, these are going to be pushed over here. We're going to have a lot of low number of successes, and we won't be likely to get 5 or 6. So in that case, the bulk of the probabilities are over here, and it will skew to the right. Okay, so I'm not going to do one like that because you can kind of see it just thinking the opposite of this, but we'll say this. When P is, well, let's just write it down, make it official here. Make another little note here. Okay, when P is less than 0.5, and we're dealing with a binomial distribution, when P is less than 0.5, the graph will be skewed right. Okay. So when we have one of these binomial distributions, we talk about the mean and the standard deviation of the distribution. There's a kind of an easy way to work with these. There's a formula we can use. And the formula is on your Chapter 5 handout, which is on Blackboard under the handout section. So you're going to want to use that. But before we get to that, I want to show you geometrically what this means. If you think of, if we could somehow take a cutout of this graph, like think of it as being on a thick piece of cardboard, this picture, and you cut out just the graph, and we want to find the balance point. So we're going to take this cutout and try to balance it. We're going to try to put our finger along the line here somewhere and balance it. So, or you could think of it like the center of gravity where this would balance. Well, geometrically, if you find that center of gravity, that corresponds to the mean. There's a mean of this distribution, which is the expected value. So the geometry of it is it's the balance point. And what it really means is, in a case like this, I'll use the free throw shooter analogy because I think it's easier to talk about. If somebody makes 80% of their free throws and they're going to take 6 shots, how many would you expect them to make on average? That's the expected value. That in this case, we're going to see it's about 4.8. So that if you had a cardboard cutout here, to make it balance, you'd have to put your finger at about 4.8. That would be the balance point. So it's not right in the middle because this thing is not symmetrical. It's going to be over at 4.8. So, so the mean has that geometric interpretation, although we don't ever really use it. We're going to be asked to find the mean and the standard deviation of a probability distribution. And we've got some formulas that we can use. Like we've got this formula here. You've seen this one, the mean, and I said a lot of times it's written this way. And the formula is x times the probability of x, so we've seen that a whole bunch of times. So you could find the mean of this distribution using this formula. Here's the hard way to do it. The hard way is to go back to the table and use this formula right here. So to find the mean, you'd start here. You'd go. So we're using x here instead of r, but it's the same thing. So we would go 0 times 0.000 plus 1 times 0.002 plus 2 times 0.005 plus 3 times 0.082, and we go all the way down the line. If we did that, we would get 4.8. The reason I know that is because there's a much easier way to do it for a binomial distribution. So this formula that we looked at earlier to find the expected value or the mean of a distribution, this formula works on all discrete distributions. But if we know we've got a particular discrete distribution, and that particular one is the binomial distribution, we've got a much easier formula, which we'll get to in just a minute. So if you are ready, I'm going to show you 2 probably the two easiest formulas in all of statistics, and they are used specifically for when you have a binomial distribution, which is what we studied in 5.2 and 5.3. The binomial distribution. It's a discrete distribution, a particular type, or a particular one, and when you have a binomial distribution and you want to find the mean of the distribution, you've got this super easy formula. If you want to find the standard deviation, it's also pretty easy, but we need a square root. So for us, we have applications that involve the mean, not really anything for the standard deviation, but some of you will see these in later classes. But the expected value, n times p, we don't have to do this. This works. This will get you the same answer, but if you know you've got a binomial distribution, I would never use this. I would never go through this table and go through all that math when you can go n times p. So for this particular distribution right here, the mean is n times p. N is 6, p is 0.8, so the mean is 4.8. What that means, remember this is sometimes called the expected value. If you're going to flip this coin 6 times, and you did it over and over and over and over, the long-term average is you're going to get 4.8 heads, long-term average. Or you could say, if somebody is going to the free throw line and they make 80% of their shots and they're going to go 6 times, on average they're going to make 4.8 of those. Now again, you're never going to make 4.8, but here's what you're going to make. You're going to make 5 quite often, right? About 39% of the time you'll make 5 shots. You'll make 6 shots about 26% of the time, and you'll make 4 shots about 25% of the time. So most of the time, this person's going to make 4, 5, or 6 baskets. Occasionally, they're going to make 1, and very rarely, they're going to make none. But this gives us the expected value or the mean. So remember, this formula here works for any discrete distribution. In this class, we only study one discrete distribution. We just study the one, just the binomial distribution. But there are others, we just don't study them in here. But this works on all of them. But if you know you've got a binomial distribution, well, you could use this, but it's much easier just to use this. These are only for the binomial distribution. Binomial distribution only. So if you want to find the standard deviation, which again is a measure of the spread of the data, then we would use this. We don't have applications for it, but the homework will probably ask you about this. One also thing I need to mention in the homework. So in the homework for this section, some of the problems that I'll ask you to do, I'll say on the homework sheet, it'll give you a number and it'll just say A, B, C. So like for instance in the homework in 5.3, I ask you to do 19 A, B, C. Well, I do it purposely because part D, skip part D. So part D, some of the newer editions of the book covered this concept of quota problems. It's just not a topic that we cover in the class. It's just a different way of asking the same sort of questions that we cover. It's just a little different. We still use binomial PDF for these kind of questions, but we're not covering them officially. So we can skip any questions about quota. So just skip the quota problem questions for part D. There's just some of them in the homework, but you'll notice it says ABC. That means just skip part D. Now I know some of you are thinking, not so fast, Kurt. I paid full price for this course. I'm going to do part D. I understand. And if you have any questions about part D, I'll be glad to go over them with you. But they're not officially covered in the class. So I referred to this Chapter 5 handout a while back. So this is one that you can have. It's not as useful as a Chapter 4 handout, but there are some things that we definitely need to mention on here. So when you look at this, we've got, in 5.1, we talk about discrete probability distributions, just generally speaking. We give this formula here that we talked about to find the mean or the expected value. And also this formula for sigma, which if you wanted to do it by hand, you could do this. So these work for any, these are general formulas. They work for any discrete probability distribution. So there's a distribution called the Poisson, which if you take another class, the second stats class, you'll probably study that. These work on that. They work on any discrete distribution. So then we've got the only one that we study in this class is the binomial probability distribution, which is a discrete distribution, the one that we study. And you've got a few different ways to figure out the probability of R successes out of N trials, which we really just use the third one here. But here's where, if you know you've got a discrete distribution, if you know you've got a binomial distribution, these formulas are much easier to use than the general formulas above. So the general formulas above work, but if you know you've got a binomial distribution, I would use these. These are much easier. Remember, these only work for the binomial probability distribution. Those formulas up above also work, but these are much easier. So, all right, so these are the ones that we've been, well, this is the one that we used. We didn't do one with this yet, but we'll do a couple homework problems where you can use this. But basically, your calculator does all the work. It's just n times p times q, and then take the square root of that. That's going to give you the standard deviation for the random variable r, which is a discrete random variable in both of these cases. This particular discrete random variable, the binomial random variable. So let's go ahead and try a few of the homework problems from section 5.3. So let's try section 5.3, homework problem number 4. And it says, consider a binomial experiment with n equals 20 trials. So you got 20 trials, probability of success 0.4. And part A says find the expected value and the standard deviation of the distribution. Okay, these are super easy to do because this is a binomial distribution. So remember, we could, if we wanted to, we could use this formula here. Right, we could use that one. And then we could use this one also. We would get the right answer, but I would not recommend using these because these are so much easier because we know it's a binomial experiment. So although these will work, these are going to be much easier. So let's not use these. If we use this first formula, n times p, we have 20 times 0.4, which is 8. And this has a very good application. It's very intuitive. Just think, let's suppose somebody is going to the free throw line. They're not very good at free throws, but they make about 40% of their shots. And this person is going to take 20 shots. Well, on average, they're going to make 8 of those shots, which makes sense, right? This 40% of 20 is 8. So on average, they'll make 8. Long-term average. Sometimes they'll make more, sometimes less, but long-term average is 8. Okay, so the mean, remember the mean is also the expected value of the distribution. So that phrase makes good sense. Now for the standard deviation, again, we don't have many applications here in this class, but we can still see it's pretty easy to figure out. N is 20, P is 0.4. If P is 0.4, what does Q have to be? It's got to be 0.6, right? P plus Q is always 1. So we just punch this in the calculator, and we get roughly 2.19. And again, if the book doesn't tell you, or a quiz or test doesn't tell you where to round, just round wherever you want to. Usually a couple decimal places is good. Make sure you round correctly though. So if you decide you're going to round to the second decimal place, make sure you round correctly. Like, don't just truncate it. Just use the standard rounding techniques. So let's see. So then number 4 has a part B. Part B says, would it be unusual to obtain fewer than 3 successes? Well, we would expect to get 8 on average. So fewer than 3, probably unusual, right? Person who makes 40% of their free throws and has taken 20 shots, fewer than 3 means 0, 1, or 2. So that's probably going to be pretty unusual. It says confirm your answer by looking at the binomial probability distribution table. Well, we don't need to do that. We can do this. We can just figure out what is the probability that R is less than or equal to 2, right? It says fewer than 3 successes. Fewer than 3 means less than or equal to 2, right? In our case, when it's discrete, that's the same as less than 3, because 2.7 doesn't make any sense. It's going to be integers, right? These are discrete distributions. And we know how to do this with binomial CDF. Remember, binomial PDF is if we have an equal sign here. CDF is if we have a less than or a greater than, with or without the equal sign. But the perfect one is less than 2, because less than 2, that means R could be 0, 1, or 2. As long as we're starting at 0, we're good to go with binomial CDF. Right? We don't need to go 1 minus because we're starting at 0. So we could just say this is equal to binomial CDF NPR NPR. Remember, CDF starts at 0, goes up to and includes this one. And if we punch this in our calculator, we're probably going to get a pretty small number. So I got 0.0036. So of course, you look in the back of the book, it's going to say 0.004, because remember the book only goes to 3 decimal places. Or actually, I guess it could say something different. Remember, the back of the book is using the tables, so they're going to get round-off errors. So they might even say 0.003. I mean, it could be a little different, but as long as we're close, we're probably fine. Our calculator just gives more precision than the tables do. So remember, when you look in the back, especially when you use binomial CDF, you could get an answer a little bit different than the back of the book. Okay, another one to take a look at is number 8. This is an assigned problem, so spoiler alert, you may want to cover your ears. But this is a good one to take a look at. So we've got A, B, C, D, E. Let's look at A, B, C, D first. So they want us to match the histograms. Remember that our book is going to call these histograms. They're really graphs of probability distributions, but they'll call it histograms. And again, they do look like histograms of several binomial distributions with 6 trials, and they want to match given probability of success with the best graph. So some of them are kind of easy, like B is 0.5. If P equals 0.5, we know we're going to have symmetry there. And D is 0.9, which is a high probability of success. So you know that we're going to have a lot of successes, so the probabilities are going to be focused on the right side of the graph, right, towards the upper end, like towards 5 and 6 successes. So there's going to be a skew left. So, but with that in mind, try them out, see what you get, and then come on back when you're done. So hopefully this is what you got. We look at part A, it says P equals 0.3. So if P equals 0.3, there's a low probability of success, so we're going to have more numbers towards the lower end. And graph number 2 shows that. Part B, P equals 0.5. We know there's going to be symmetry right there, and graph 1 shows that symmetry perfectly. Part C, P equals 0.65, so it's a little bit higher success than like a 0.5, so there's going to be a little bit more of the probabilities focused on the right side of the graph, and there'll be a little bit of a skew left, and that is reflected best in graph 3. And then finally part D, 90% success rate. When P equals 0.9, there's going to be a lot of the probabilities focused on the far right of the graph, so they have a skew left, and that is reflected in graph 4. And then part E, I'll just kind of walk through this one. It says, in general, when the probability of success P is close to 0.5, would you say that the graph is more symmetric or more skewed? It's definitely more symmetric when it's close to 0.5, right? Then it says, in general, when the probability of success P is close to 1, would you say that the graph is skewed to the right or skewed to the left? It's definitely going to be skewed left. That's like reflected in 8 part D. What about when P is close to 0? So you've got a small rate of success. It means there's going to be very few successes and a lot of failures. Well, so shouldn't have really said a lot of failures. There will be, but when P is close to 0, you're going to get a lot of small successes, like a lot of R equals 0, a lot of R equals 1, and you're going to have hardly any R equals 6 or R equals 5. So the probabilities are going to be built up on the left of the graph, and then it'll be skewed to the right. And then there's one more we should take a look at. That's number 23. And 23 is a really good one to look at because the wording's a little strange on this one. And so this is definitely a good one to take a look at. So this one is talking about property crime. And it says the FBI Standard Survey of Crime shows that for about 80% of all property crime, the criminals are never found and the case is never solved. So here's the thing that's strange about this. They're talking about crimes not being solved, but if you look at all the questions, like part A says, what is the probability that none of the crimes will be solved? Part B, they're talking about at least one crime will be solved. C, what is the expected number that will be solved? So the note for this problem is they keep saying will be solved. So even though they ask us, they give us information, they say 80% won't be solved, since they keep asking about will be solved, what we should do is figure out, let P equal the probability that it will be solved, which is 0.2, and let Q equal 0.8. So this means it will be solved. So again, the reason I mention this is because they mention 80%, so it looks like we'd say, okay, P is 0.8, but then every single question asks about whether a crime will be solved. So it's a little tricky, but I would definitely use P equals 0.2, the probability that a crime will be solved, because they tell us 80% of them will not be solved, which means 20% will be solved. And then we can just use P equals 0.2 for all the questions, because the questions all keep asking about whether a crime will be solved. So later in the sentence, or in the paragraph, it says the police are investigating 6 property crimes. So I'm just going to move this up. I'm going to say N equals 6. So we've got P equals 0.2, N equals 6. And then we can go through the questions. So part A says, what is the probability that none of the crimes will be solved? So what is the probability that R equals 0? And we can just use binomial PDF, right? We use PDF when R equals a number, R equals 0. And this is just going to be NPR. And we can just punch this in the calculator. So when I punch this in, I got 0.262144. In the back of the book, they would most likely say 0.262. Okay, but either of those are fine, however you want to do it. Then part B says, what is the probability that at least one crime will be solved? Okay, here we go. At least one. At least one means R is greater than or equal to 1, right? This means at least one, meaning R could be 1, 2, 3, 4, 5, or 6, meaning the only thing R can't be is 0. That's the only thing it couldn't be. So we could use binomial PDF repeatedly for 1, 2, 3, and then add them all up. We can't use binomial CDF directly because CDF won't let us start at 1 and go to 6. So what we typically do instead is we go 1 minus the probability that R equals 0. Right? Because that gets the only one that's not counted here. This gets 1 through 6, the only thing missing is 0. Well, we know if we add up all of these and 0, we have to get 1. So that's why we do this complement rule. Whenever it's a greater than or equal to or greater than, we need 1 minus. Remember? Greater than or equal to, we need 1 minus because binomial CDF doesn't let us start at 1 and go to 6. So then we would just go, for this one, 1 minus binomial PDF and PR, which is a problem we just did. So basically get 1 minus 0.262. And we get 0.738 if we do it like that, if we do this math. So of course you could just put this in your calculator and you get essentially the same thing, just get more decimal places. Okay, so hopefully you guys are okay with this. Whenever there's a greater than symbol here, and we're using a binomial distribution, we have to go 1 minus, oh my gosh, let's see, PDF, yep. We have to go 1 minus. So I mentioned this before, but sometimes people will use CDF here, and you get the same thing. It's only because of the 0, because cumulative doesn't have anything to add up yet, because it starts at 0, okay? So sometimes students will mention, hey, I use CDF and I got the same thing. It's only because it's a 0. As soon as you put a 1 here, or anything other than 0, then PDF and CDF are going to give you different numbers. Okay, so then part C says, what is the expected number of crimes that will be solved? And what is the standard deviation? Well, the expected number is just mu, right? N times P. So N is 6, P is 0.2, which means 1.2, which is not too many, right? That just means if you did this over and over and over, the same situation, out of 6 crimes, on average, you're going to solve 1.2 of them. Then the standard deviation is just NPQ. And when we plug these in, N, P, Q, and take the square root, get right around 0.98. And they'll ask us to find this even though we don't have many applications. Although this mu makes sense, right? We've got an application, like on average, how many crimes will we expect to solve? This is just a measure of spread. We don't really have an application for it. Then part D is a quota problem, which we don't have to do, but it talks about them in the book. If you're curious, you can see how those work. So that should get you started. And of course, if you have any questions, just let me know.